All right, welcome everybody to lesson 3.3, the study of logarithmic properties and their graphs. So I have a really long quote here. If you really want to read it, go ahead and push pause. The guy that's kind of the bane of everybody's kind of doesn't really like this guy. Is he's invented the logarithms. Logarithms themselves are not very complicated, but for some reason there's just some confusion that goes on throughout the study of logarithms. But I think we can get through all of them. All right, so the logarithm in general is the inverse of the exponential function. So we always start with the exponential and then we look at the logarithm because they're basically family. They're inverses of one another. Okay, so the first statement here is if x is greater than 0 and b is greater than 0 but not 1, we have a very basic statement of y is equal to log base b of x if and only if b to the power of y. So notice this, b here as the base to the power of y is equal to x. So notice I said the word base b, log base b, exponential base b. Go across the equal sign to get the exponent for the base in the exponential piece, or for the exponent. Okay, so base b to the power of y is equal to x. So a couple statements we can make here, going between logarithmic and exponential form. We could say that log base 2 of 8 is equal to 3 because we know the other side is true. The opposite of this is true, or the inverse of this is true. We can look at the exponential base 2 because it's log base 2. We can say that this is 2 to the power of 3. So notice 2 to the power of 3 is 8. And we know that to be true. 2 cubed is 8. So these two statements are true. You can see that we can go back and forth between the two types of functions. We could also go the other direction. If I told you 2 to the third power is 8, you could rewrite that in logarithmic form as log base 2 of 8 equals 3. Okay, so another simple example here is log base 5 of radical 5 is equal to 1/2. Now, you can write this out really quick before I write it out. You can pause, take a second to write it before I write it if you want to see if you're getting this right away. I know these are only two examples, but I think this is so straightforward that I think we can all get it pretty quick. Okay, I think I talked enough right there. So log base 5 of radical 5 equals 1/2 because changing it to exponential, we know that 5 to the 1/2 power is equal to radical 5. And we know that's true. We know our half exponent means radicals. Okay, so that's our other true statement there. Okay, changing from logarithmic to exponential forms because they are inverses of one another. Okay, so a couple of basic properties that we need to know in order to do some of these logarithms fast without a calculator. And this is the goal. One of the goals for me is always to get you guys to know how to do stuff without a calculator. So the first one is using our logarithmic properties to solve equations. So the first one is log base b of 1. And this is just meaning any base that we use. Log base 20, log base 50, log base a billion, all that sort of stuff. When I say the log base b of 1, it's always going to come out the same number. And we can think about that as changing into an exponential function. I don't know what this blank spot is, so I'm just going to let it be a variable for right now. So I'm basically saying, hey, b to what power equals 1? Well, I hope you all know this, and I hope you all said the answer already. We already know that anything to the 0 power is 1. That means log base b of 1 is equal to 0 every single time, always. And then likewise, we go back into the log base b of b, and we just kind of do the same thing. I don't know what the answer is, so I use a variable, and I say, well, base b to the power of x is equal to b. Well, we know that b to the first power is b, because this really is b to the first power. That means this is 1. So log base 2 of 2 is 1. Log base 5 of 5 is 1. And that actually goes right into the next property, saying log base b of b to the y power, whatever that exponent is on that b. And we just look at it like this. We say, okay, well, b to some power is equal to b to the y. Well, this statement shows that my exponents have to be the same. So that means this is actually just y. So log base 2 of 2 to the third is 3. And we can do this anything. I'll show an example here in just a second of this type of property and a couple of other ones. And then this last property is kind of the use of inverses. This property says b to the power of log base b. Well, I know that's not exactly what it looks like right now, but that actually is supposed to be a base b. So it's b to the power of log base b of x. Well, we know inverses undo each other, which means the exponential base b here and the logarithmic base b will cancel each other out, and we're left with whatever's inside that thing, and in this case, it's just x. So that's our answer. That's our 4 basic properties that we're going to use to help us out in order to do this stuff without a calculator. Do some of it. You can't always do all of it without a calculator. Try to do as much as we can, because it actually makes you a faster mathematician. Okay? So there are, I know I'm going to say it, there's calculator stuff here. So if you have a calculator, even if you have your phone right now, try to get it out, see if you can find the logarithmic button on the calculators, the 83s, the 84s. It's usually down towards the bottom left, I believe, off the top of my head. I, for some reason, don't have one in front of me. Don't know why. It's weird. But I do have a calculator on my phone, and all of you guys do as well. I know you're not supposed to use it in class, but if you're ever out there in the real world and you need to know something about logarithms, I can't tell you where, you might need to do that, but whatever. If you rotate your phone sideways, you will get a scientific calculator. And if you didn't know that already, you're welcome, because some people didn't know that. And maybe it was you. Okay, so the first logarithm that's on your calculator, we actually have 2 of them. The first one's called the common log, and this is base 10. Okay, and it looks like this. Notice there's no base written. It's like multiplying by 1. We don't write the 1. Whenever I say 1x, we just write it as an x because we don't need the 1. It's the same thing here. This actually is read as log base 10 of 100. Well, I know what this is already, but I'm going to use one of my properties. Log base 10 of 100, I can actually rewrite as log base 10 of 10 squared. Well, our property says that those two things cancel each other out, basically. Log base 10 and exponential base 10 will cancel each other out to a big fat 2. Okay, so log of 100. You can verify this on your calculator if you need to, but if you plugged in log of 10 on your calculator, you'll get out of 2. Now this one you have to plug in your plug into your calculator. So hopefully you found your logarithm button somewhere already. And when I did this on my calculator, I get 1.5. See, there's my big decimal point, 54. Actually, 0.5378, blah, 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 right? So rounding to 1.54. And plugging in the calculator should be pretty easy. Okay, so if you're kind of in the location of finding the things on your calculator for logarithm, you might notice another button there, and this is what's called our natural logarithm. Okay, so the ln, this right here is the ln. That's not a 1. You need to be very careful with that. This is the natural logarithm, so ln. It's like Latin for like logarithmic natural or something like that. I don't remember exactly, but something like that. So it's the natural log, and natural log is base e, and it's another one where we don't write the base. We just know whenever we see ln, it's automatically base e. So the first example that I have here, this is the logarithmic base e of e. Well, our first property says that is, or not our first property, our second property that we had there says that is a 1 because, again, they kind of cancel each other out. And the same thing goes for our second example here. The natural log of e to the third power. Again, the e's are going to cancel with, or the e is going to cancel with the logarithm, the natural logarithm, and we're going to be left with that exponent. And the last one here is kind of an example of that last property where we have exponential base e and logarithm base e of 4. So we have e to the power of the natural log of 4, and again, those are going to cancel each other out, and we're going to be left with a 4. All right, pretty straightforward, trying to plug things in. If you want to plug something in your calculator just to see what natural log does, you can try to plug in maybe the natural log of 4. See what that comes out to. Ugly 4. Ugly parentheses too. Man. Whatever. So you take the natural log of 4 and figure out what that is on your calculator, so you can kind of use the button. And what you'll notice is right there with the natural logarithms, or actually both the logarithms, are their inverses. So 10 to the power of blank. I think you guys have 10 to the x power. And the natural log has e to the blank, e to the x power right next to it. Okay, so they're right there together because the guys who created the calculators knew what they were doing. They know their inverses, so they put them together. Okay, so moving forward right along here, solving simple. We're going to solve simple equations today. We get a little bit harder equations later using more and more properties of our logarithms and using them to solve. But right now, we use a very basic, very, very basic use of exponential functions to solve these problems. Now, this might look challenging to you because you have to find an x value that makes this true. But if we changed it to exponential functions, or an exponential function, we'd actually get a pretty quick answer here. This is log base 10, the common log, and so I can rewrite it in exponential as saying 10 to the power of 5 is equal to x. Well, the goal is to find x. Well, I just found x. X is 10 to the 5th. So I can say, okay, well, I'm going to make it 10 to the 5th. 10 to the 5th is 10 or 100,000. Look at me write all these zeros. Really, really sloppy. But you get the idea. Okay, so that's 10 to the 5th, x is equal to 100,000, and that's your answer. So if you took the log of 100,000 on your calculator, you would get 5. Okay, so likewise in this next example, this was actually pretty quick. Some of you guys that caught on to that first one, you're going to give me an answer to this so quickly that it's almost pointless to rewrite this. But I'm going to rewrite it for those of you that didn't quite get there. So this is log base 2 of x is equal to 3. I'm going to rewrite it in exponential form. I'm going to say this is actually 2 to the power of 3 equals x. Well, 2 to the power of 3 is 8, which straight away gives me my answer. That's why these are kind of our simple logarithmic equations. Okay, and these are ones that we can just do super quick. Later ones get a little bit harder. A little bit better in my terms, actually. All right, so the graphs. This is the last thing. This is kind of what everybody's been waiting for because they love the graphs. I know you do. I know you've been out there just sitting there waiting for them. The graphs, if you can, if you're already thinking about the fact that this is an inverse of the exponential function, you might remember that inverse functions reflect across the line y equals x. And if we already know what the graph of an exponential function looks like, we can just swap our x and y values and regraph. That's what it means to be inverse, is we swap our x and y values. And there are a few things that go along with this. We have a parent function kind of, just like exponential functions, we don't truly have a parent function. It all depends on the base that you're using. So like a parent, we have like log base 2 would be a parent function for all log base 2's. And the log base 5 would be the parent function for all log base 5's. You have to depend on the number itself, just like when we did our exponential functions. So whatever parent function you're using, the vertical asymptote is x equals 0. And that should be kind of obvious because the exponential function had a horizontal asymptote of y equals 0. And it's also going to be reflected across the line y equals x and becomes the line x equals 0. And then the exponential function had a point 0, comma 1 as what we called our initial value. Well, that point gets flipped and becomes the point 1, 0. I know I just skipped a step, but I'll get there in a second. Okay, so that point gets flipped, and we can just end up flipping all the points from the exponential graph, the piece that we already kind of know. The last thing there that I kind of skipped over there accidentally is the domain for logarithmic functions. For the parent function, it's x is greater than 0. We cannot take the logarithm of a negative number. It is not defined for negative numbers. We can only take the logarithm of positive numbers. We can't even take the logarithm of 0. It's impossible. But we can take the logarithm of positive numbers. That means anything inside the logarithm has to be positive. So if we're trying to find domains of stuff, we can kind of look at just the thing inside the logarithm has to be bigger than 0, and that'll find our domain. Okay, so I'm going to create a very, very small video in just a moment, and that you guys can have right after this, that will show you graphs of the logarithmic functions and what they look like and what the transformations look like. This is just the PowerPoint video, and then I'll go to my example video that goes right along with this. So the assignment here, this is something that we're going to be starting now, where I'm going to give you a large assignment and only a part of it will be due by the end of class. Okay, so I have 7 problems here in bold that will be due to me by the end of class on Monday, I believe it's the 19th. Yeah, the 19th. Okay, so at the end of class on Monday the 19th, those 7 in bold will be due, and the rest is up to you whether or not you do it, but I strongly encourage that you do them. All right, so leave any comments you might have about the video in the comment bar. You can email me, all that sort of fun stuff, or you can just wait and tell me on Monday how it went. All right, so I'll see you later. Hope you had fun. Hope I didn't put you to sleep. But some of you need to stop watching these videos at like 1 a.m. So I'll see you guys in a little bit.